Good morning. It's December, and we're going to do a lot of math during December. So get excited. Our first thing is the overview for what we call rate of change. That's the unit that I would like to finish. It looks like this in the textbook. We're going to get to know this guy. It looks like this in your gradebook. Rate of change overview worksheet. I want to go ahead and do this boring part because I want you to see how I do it. I clicked on it, it downloads, it goes to a bar like this that says I just downloaded it. Now I use Kami up here. I open up an entirely new tab that's in Kami and I'm like, well, what do you want to open up? I think I'm going to open up something from the computer, maybe something I just downloaded. And voila, there's the assignment. There are a whole bunch of graphs to sketch. Notice they made a graph right here. I'm going to go ahead and write distance and time, and I'm going to make my own graph that looks like that. I'm going to copy it a bunch of times to save us time. You may want to do this as well. It will save you time if you think about what needs to happen. There's one direction. And come on, there you are. All right, so now I've got this. I'm gonna move you over a tiny bit. Look at that beautiful graph. And I'm gonna put in, like they had there, they had time that they were keeping track of down here. We have distance that we're keeping track of up here. This is all just kind of legwork, but the nice thing is now that I've got that, I can go up to select, I can click this thing right here, and oh, I might as well click that there. And I can click on this, and now I can scan that, Control C, go down here, Control V, oops, oh, Control Z, Control View. I got that arrow, I can put it down in here, and voila, got it again, and Control View, use the arrow to put it down here. Oh, is that all of them? Yep, okay, great. Okay, so now I've got my graphs in. Just wanted to do that before we get into the talking part. So that's something you can do to set it up, distance from the detector. And we'll talk about what that even means right now. So we're going to create graphs about Terrence. Well, who's Terrence, you ask? Good question. Let's talk about this Terrence fellow. There he is. Terrence is a great skateboarder, or at least Terrence is working on his skateboarding skills. I can click on the thing and we have this motion detector. It figures out how far he is from it. So watch. If I go to the right, he's further from it. If I go to left, he's closer to it. And if I go back and forth really fast, he goes further and closer and further and closer. Oh my gosh, this is a graph of how far Terrence was, or how close Terrence was to the motion detector. Clearly he was right next to the motion detector right here. He was way far away from the motion detector over there. And that's what's going on, okay? So we are going to do different things with Terrence, and we're going to get different graphs. So let's see what they want us to do here. It says first, create a graph that shows Terrence moving away from the motion detector at a steady rate. Describe this graph. Okay, let's do that. Let's take Terrence again. I'm going to reset this thing. Hey, reset. There we are. And I'm going to move steadily away like this. It's going really slow. What does the graph look like? Well, you'll notice that it's pretty steadily going up. Let's see if we can be even more steady. And 1. There. Now notice that makes a pretty darn straight line. That's a very important thing. That's the first thing we're going to discuss in this chapter is straight lines. What does a straight line mean? Well, in where I'm going to draw it so it looks more like what we had, because it wasn't a perfectly straight line. We're going to describe that in words. What is going on with that? Well, the line is pretty much straight. It goes, increases slowly. Matching how slowly Terence was ruling on the skateboard. The really important thing you need to notice right now that we're going to talk about a lot in this section is it's a straight line. It is increasing. Why was it increasing? Well, the distance is getting more. So it is increasing because he is rolling away from the motion detector. Hope I explained the motion detector enough. We'll get to play with it some more. All right, so now we've got to create one in which he stands still. Let's see what that looks like. This is going to be boring. I'm going to click on him, put him down, stand still. Wait, come on. There we are. What is going on with that? Well, you can see the line doesn't go up because he's not moving away from the motion detector. And the line doesn't go down because he's not moving toward the motion detector. So in the end, the line doesn't move up or down. It stays perfectly horizontal. And that's what we need to say. So let me put this line in. We're going to draw it. Again, I don't mind if the sketch is drawn. Yep, because this is an imperfect world we live in, and it's okay not to have a line that's perfectly straight in this case. Just don't have it going like, that doesn't make any sense. We're trying to draw a horizontal line. Okay, so what's going on with this one? We're going to say the line in the graph doesn't go up or down because Terence isn't moving toward, away or from, away from or toward the motion detector. So we get a horizontal line. Horizontal line. Remember, a good way to remember the word horizontal, which direction it goes, is it has the word horizon in it. It goes the same direction as the horizon, sideways. All right, and there we go. Look at that. We just described it in words. Okay, create a graph that shows Terence moving toward the motion detector. Oh, I guess he was moving away from before. Let's move toward. Describe this graph. Okay. I'm going to start over here. It doesn't say. Notice when I slow down, the line gets less steep. When he stopped at the end, it went horizontal. So the faster he's going, the steeper the line gets. Let's try that again. If I go really slow, it barely goes down at all. But if I go faster, it gets steeper. That's an important thing to realize. Okay, but we're going to use the first one. I'll do it one more time so we have something to copy. Whoa. like that. That's fine. Okay, let's go draw it. I'm gonna draw in black. It started way up here and it went something like that. I don't know. Notice it's not perfectly straight. That's okay. Now, what would make it straight is if he stays the same speed. Faster is steeper. Slower is a shallower curve, a steepness of the graph. And that's one reason we care so much about teaching you slope. Because when you start talking about real world things, it represents something. In fact, what is it keeping track of? The steepness of the line while I type this? Think about that, or, well, think about one thing at a time. The line is decreasing because the distance between Terence and the motion detector is also getting smaller because he is skating toward it. Once you get the hang of this stuff, it's like really, really simple. You're like, wait, that's all? Yes, yes, that's all. We're just describing what's going on, and he's getting closer to the motion detector, and so the line gets lower and lower because the distance between them is smaller and smaller. He is skating faster along the steepness of the line. Can't spell, but increases. And that's good enough. So notice, steep means he's going fast, shallow means he's going slow. So he's like fast, slower, fast, slower, fast, and slowing down. And you can see a lot from the steepness of the line. That's really important in later math. In calculus, we spend a large amount of time learning how to deal with the steepness of a line that changes. Okay, in this class, you deal with mostly with steepnesses of lines that don't change, so perfectly straight ones, and that's what we call slope. But later you'll learn how to find the slope at any point on something like this, but that's a calculus trick. Okay, think about the shape of the graph shown. Describe how a skateboarder should move to match this graph. Test your thing. So let's guess, well, I'm not guessing because I know what we're doing. Notice he's moving away from it because the distance is getting further and further between them. And then he moves back toward it. And it starts out steeper and then slows down and then just gets steep again. So it looks like he starts out going fast, slows down a bit because it's not as steep up here. And then it gets steeper and steeper, so he speeds up again. Let's see if we can make that. Boom. So we start out over here and he speeds up and he slows down. Oops, I went the wrong way. I kept going away. Let's try that again. Right here, click. Fast, slowing down, and fast again. Not perfect, but it goes up, goes down. So he goes away from and back toward. Do we have to make it perfectly the same? No, you could spend a long time. He skates away, slowing to a stop. Then he skates toward the motion detector, speeding up as he goes. That would work. Is that the only way to say no? This is a really important type of graph called a parabola. Well, it kind of looks like a parabola. It might be. It's hard to tell just from looking. But that's a very important one because that's the type of graph that models gravity. Well, here's a fun one. Look at this shape. How could we do this? He starts out far away and he gets closer the whole time. He starts out going really fast and then he slows down as we go. So let's see if we can make that. So he's going to start out far away. He's going to go fast and then slow down toward the end. Okay, we're going to start over here. We're going to go fast and then slow. I don't think I was fast enough. Let's try again. You remember you can log into here as well. Fast. And then slow. It's almost like he's trying not to get to the end. That's pretty close. Let's take a look at what we got. Oops. Yeah. All right, so he starts far away. Heading toward the motion detector very fast. Then slows down more and more as he gets closer to it. Because not only is he always getting closer, which means the line's always going down, the distance between them is getting smaller, but also the distance was getting smaller really fast, which means he's getting fast, but then slower and slower. All right. All right, so the previous questions, either description of or graph is given with the skater's behavior. You were asked to sketch a graph and describe the graph. In other words, great. Now pretend that you and your friend have a motion detector. Describe the path that you want your friend to walk, making it different from any of the above. Sketch the graph. Let's see. What do we want him to do? We want him to we'll go we'll have him go to the left, slowly to the right, and back to the left really fast. We'll do that again. So fast to the left and slow to the right. That's our goal. Fast to the left, slow to the right, and then fast to the left again. Notice fast is steep. So we're going to say, oh, this is one that I'm arbitrarily picking. You could do whatever you want. He skates quickly toward the motion detector, then slowly away from it, then back toward it. We're going to say notice quick, steep, slowly, shallow. It's a very important thing to realize. So understanding what steep and shallow graphs mean is really important. So I end up with a graph. What did we have? We had him in the middle. He skated steep, and then slow, and then steep. That's good enough. Well, actually, no. The steep one looks about the same steepness as the slope. Steep. Steep. Like that. That'll work. Because the steep ones that go down are steeper than the shallow one that goes up. All right, there we are. We did that. Now describe a path that is very different from the graph of the previous question. Sketch that graph. Okay, let's do that. Let's try, I don't know, we're gonna go left, right, left, right, left, right, left. So he skates to the left, right, left, right, left, right. Each time he goes a little further from the center, 4 feet, okay? Notice he has to go faster and faster each time too, doesn't he? So this is just a little bit to the left, a little bit to the right, but then further and further and further and further and further until he gets back to where the motion detector is. All right, let's type that in. Oops. Almost done, by the way. This is the last one. And then I'll type something in here that you should know. We'll call it good. Okay. He skates back and forth a little further each time. He has to skate faster and faster to get that. All right. So we started in the middle, went down and up and down and up and down and up and down. Oops, that's terrible. Let's try that again. Down and up and down and up and down and up and down. Perfect. That'll work. When we have a graph that goes back and forth like that, if it does it in a regular way, we call that a periodic graph because it does the same thing over and over, which we call that a period of time. It's a repeating period of time. Regardless, here's some stuff that you can come away with. Steep. Well, we just already said steep meant fast and shallow meant slow, right? Which means steepness, the steepness of the graph, speed. Now that's a really important thing. Steepness in this graph is speed. Now what are the two things that we keep track of in speed? Well, if I'm talking about the speed of your car, I was talking miles per hour, which means miles divided by hours. Distance is miles, time is hours. So distance divided by time. Distance divided by time, right? In other words, steepness is always, what do we have on the distance? We had y as the distance axis and time is the other axis, right? Steepness is distance divided by time. That's y divided by x. Y divided by x. Now, this is kind of cool. This is a really weird thing. You don't have to get this all right at once, but this is a big concept that we're going to keep pounding into your brain until it sticks. Steepness in this particular situation is speed. But in every single possible graph, the steepness of the graph can be described by y over x, which is how we do speed, distance divided by time. But if we had other things, it would be like, I don't know, this divided by that. We always have y divided by x when we're talking about the steepness of the graph. What do we call that? We can call that rate of change. We can also call it So just remember, I mean, we sorry, I'm going to put quotation marks around this. Whenever we make a graph for the rest of eternity, we divide this by that, we get the slope. We get what the slope represents. So we're going to talk about slope of lines as their own little thing. But as soon as you put it in a real life situation, it represents something. And that is a big, big deal in math. All right. And that's all the information you need to write down. I hope that that's easy. I'm going to stop sharing this. And I'm going to stop recording this. Merry early Christmas.